FET has two important characteristics. They are one commonly known as output characteristic, also known as drain characteristic, and the other is mutual characteristic, also known as transfer characteristic. Now, to plot these characteristics, how the circuit setup should be, that we will see now. So students, this is a circuit arrangement to plot the drain characteristics. Of course, even to plot the transfer characteristic also, we use the same circuit. So in this, as if you remember, when we discussed the working of FET, I had introduced all these sources, VGG, the biasing supply, VGS, it is nothing but the voltage across the gate and the source, VDD, the biasing supply on the other side, and VDS is nothing but the voltage across the drain and the source terminal. ID is the ammeter that we are connecting here to measure the drain current. I have named it as IT. Okay. Now, having this basic circuit setup, we will see how to plot the drain characteristic. The drain characteristic is nothing but the plot between drain current ID and the drain to source voltage VDS for a constant gate to source voltage, that is VGS. So how we plot this is, we set VGS to a particular value. Now how we set VGS is with the help of VGG. So we vary VGG and we set VGS to a particular value. Say for example, initially I will set it to 0 volt. This is just an example value. So I'm setting it initially to 0 volt. Now what I do is, I come this side, I vary VDD. And why I vary VDD is to set VDS. So say for example, in the first trial, I will set it somewhere at 0.5 volts. So to set this VDS to 0.5 volts, I have to vary VDD. And then for that value of VDS, I note down what is the corresponding ID, that is drain current value. Now like this, once I check it out for 0.5 volts, then I go for the next trial. Say for example, that will be for 1 volt of VDS. So for this again, I go to VDD, I change this such that VDS now becomes 1 volt. Then again, for this 1 volt of VDS, I will note the corresponding value of ID. Like this, I repeat the procedure for different values of VDS, and for every value of VDS, I will note down the corresponding value of ID. So now I go to the graph. What I do is, I plot a graph wherein I take the drain current along the vertical axis, that is nothing but the y-axis, and VDS is plotted along the horizontal axis, that is nothing but the x-axis. Now here students, what I do is, my first graph, what I plot for VDS against ID, keeping VGS at a constant value. Remember, I told you that I have set VGS at 0 volt. So for that trial, when I plot the graph, this is how I get the characteristic curve. After this, what I do is, now I set this VGS value to a different value. Say for example, now I go for minus 1 volt. Please bear in mind, VGS, it is a reverse biasing supply. Using this voltage, actually we are reverse biasing the gate and the source junction. So that is why this is in the negative scale. So in the second trial, what I have done is, I have set VGS at minus 1 volt. We will observe this by getting back to the circuit. So now in this trial, what we are doing is, we are setting VGS to minus 1 volt. Remember, initially it was set at 0 volt. Now we are changing it to minus 1 volt. So how we change this to minus 1 volt is by varying VGG. So we change VGG and we set VGS to be equal to minus 1 volt. So once we set VGS at minus 1 volt, then what we do is, again we start varying VDD from the beginning, that is from 0 volt, and for every value we make a note of VDS. Say for example, in the first trial we will set VDD such that VDS will be 0 volt, and we make a note of the corresponding drain current. In the next trial, we will again vary VDD such that VDS will be equal to say 0.5 volt, Then again for that make a note of the drain current. Then again change VDD, again come to VDS may be equal to 1 volt, again note down ID. So this process repeats for several good number of trials. And then when we plot the graph, we get the graph something like this. So if you observe this first graph, it is for the first trial with VGS equal to 0 volt. The second graph is for the second trial with VGS set at minus 1 volt. So this is the characteristic curve that we get. Like this, we keep on repeating the experiment for different values of VGS, say minus 2, minus 3 and minus 4. So for each of these values of VGS, we get different curves like this. This is the characteristic curve for VGS equal to minus 4 volts. When it is VGS set at minus 3, this is the characteristic curve here. Like this it goes. And when we set VGS at minus 2 volt, the characteristic curve is something like this. So here I can see 5 different characteristic curves which are plotted for 5 different values of VGS. So this is the drain characteristic. Now students, we will study the different regions of this particular characteristic curve. The first region being the ohmic region. Here in this part of the characteristic curve, here you can see that the behavior of the particular component is very much linear. It is nothing but similar to the VI characteristic that you learned of a resistor last year. And since here the VI characteristic is very much linear, similar to that of a resistor, you call this particular region as the ohmic region. And this point, let me name some of the points here. I have taken the origin as O. This point I name it as A. This will be B. And this end I name it as C. Now the point A is called as the knee voltage. That will be somewhere here. Moving to the next region, it is the cutoff region here. So the region in this particular area, this is known as the cutoff region. The next region is the saturation region. The saturation region exists almost from this part to this part. That is the entire region. This entire region, it is known as the saturation region. Now if you observe in the saturation region, the current ID is almost like constant for any varying value of VDS. So as you travel along this particular axis, the value of VDS keeps on changing, but if you observe when you travel along the vertical axis, there is no much change in the value of ID for any change in the value of VDS. So in this region, we consider that the drain current is almost constant. So this region is known as the saturation region, and here ID is almost independent of the drain to source voltage. The drain current in this region is given by Shockley's equation that I will discuss shortly. But before that, let me complete the last region, that is the breakdown region. This region is known as breakdown region, wherein if I further increase the voltage VTS, the component undergoes damage. So it is always advisable to use the component well within this breakdown region. And also there is another small region here which we call it as the plot between the points A and B. This is a nonlinear region wherein ID increases in accordance with the square law. And the region extends up to the point B, which is called as pinch off point. So this point B, it is known as the pinch off point. The current in the saturation region is given by the equation ID is equal to IDSS into 1 minus VGS by VP whole square. This is also known as Shockley's equation, and here ID is nothing but the drain current, IDSS is the drain to source saturation current, VGS is the gate to source voltage, and VP is the pinch off voltage. So this equation is one of the important equations which defines the amount of drain current in terms of IDSS, VGS and VP. Now moving to the next characteristic, that is transfer characteristics. As I told you, the circuit setup is the same. And here the transfer characteristic is nothing but a plot of drain current and VGS, that is gate to source voltage, keeping VDS constant, that is drain to source voltage is kept constant. Just compare it with drain characteristics, students. There it was plot of drain current, of course, but then the drain current was plotted against the drain to source voltage, keeping gate to source voltage constant. Here we have changed both the voltages. The drain current is the same, but we are now plotting the variation of the drain current depending on the gate to source voltage, and we keep the drain to source voltage constant here. So that means to plot one trial of the graph, what I do is initially I will set the value of VDS, and as I told you before, if I have to set the value of VDS, what I will do is I will take the help of VDD. So by varying VDD, I will set the value of VDS, and once I am done with setting the value of drain to source voltage, what I will do is I will vary VGS, that is gate to source voltage. And how I vary VGS is with the help of VGG. So every time I vary VGG, VGS will change, and for every single value of VGS that I set up, I make a note of the corresponding value of drain current. Now, when I plot the graph of this, I get the graph something like this. Observe here, when ID is equal to 0 milliamps, the value of VGS is equal to VP. VP, as I told you, is nothing but the pinch off voltage. So if I have to define pinch off voltage in terms of VGS, I can tell it as the particular value of VGS, that is gate to source voltage, for which the drain current becomes equal to 0. Please make a note here. When I tell ID is equal to 0, it is not exactly 0, it is at some minimum value. If you remember, I had already explained this in the first part of the video on FET, wherein we were discussing the working of FET. This particular point will tell us the value of IDSS. IDSS is nothing but again drain to source saturation current. Next, we move to the parameters of FET. Here, you would mainly study 5 parameters, that is dynamic drain resistance represented by RD, drain to source saturation current. We have discussed this already in the operation of FET, that is IDSS, and mutual conductance or transconductance represented by GM. The next is pinch off voltage, VP. This also we had discussed during the first video of mine, that is in the operation of FET. And the last one is amplification factor. Now we will see each of these in detail. First is the dynamic drain resistance. Students, whenever we tell dynamic, it represents or it resembles the AC part. So if you remember, even in your last year, in the VI characteristic of semiconductor diode, you had studied two types of resistance. One was static resistance, the other is dynamic. Static, we related it to DC, and dynamic, we related it to AC. Similarly, here also, we talk about the dynamic drain resistance with relation to the AC. So now here it is defined as a change in VDS. Observe, when I tell change, that time itself I am referring to the AC content there. So here change in VDS to the corresponding change in drain current at constant VGS is what is RD, that is drain resistance. The formula is given like this: RD is equal to delta VDS by delta ID. Observe the vertical line here. This is a symbolic representation stating that the VGS value is constant. We read this as RD is equal to delta VDS by delta ID at constant VGS. The unit of this particular dynamic drain resistance is nothing but ohms, as it is a ratio of V by I. Moving to the next parameter, that is IDSS, drain to source saturation current. This is the saturation drain current when VGS becomes equal to 0. The next one is mutual conductance or transconductance, represented by GM. Here again, this is the representation in terms of AC. And the formula is given as GM is equal to delta ID by delta VGS at constant VDS. Observe, I am using the same symbol here for constant VDS. Now the unit of this is Siemens, because it is nothing but the reciprocal of resistance. If you observe, R is given as, or resistance is given as a ratio of V by I, whereas here I am taking the reciprocal of that, and hence I call this as the conductance parameter. Moving to the next one, it is pinch-off voltage. Now students, pinch-off voltage can be defined in two different ways. One, it is the minimum VGS which results in zero drain current, and the second one is defined as the minimum VDS at which the drain current becomes constant for a given value of VGS. If you remember, during the explanation of working of FET, I had used both these circuits. Accordingly, we can define the pinch-off voltage as 1. It is a minimum VGS which results in zero drain current, and the other possible way of defining it is as the minimum VDS at which the drain current becomes almost constant for a given value of VGS. Moving on to the last parameter, that is amplification factor, represented by mu. It is defined as the ratio of small change in the drain to source voltage to the corresponding change in the gate to source voltage for a constant value of ID, represented as mu is equal to delta VDS by delta VGS at constant ID. Now students, can you tell me what is the unit of this? It is a ratio of voltage by voltage, hence mu is just a number, it has no unit. Now let's come to one important part of this particular chapter, that is the relation between mu, RD and GM. Students, I just now told you that mu is nothing but the ratio of change in the drain to source voltage to the corresponding change in the gate to source voltage. Now what I do is I multiply and divide this ratio by delta ID. So when I multiply, I get an equation like this. But we have already studied that RD is given as delta VDS by delta ID. That is, observe, delta VDS by delta ID. Also, GM is given as delta ID by delta VGS. That means delta ID by delta VGS. So accordingly, replacing these two formula in this equation, we get mu is equal to delta VDS by delta ID into delta ID by delta VGS. That is nothing but mu is equal to GM into RD or RD into GM. Students, please observe, this particular derivation is a very important part of this particular chapter and is most of the times targeted in your exam for 3 marks. So be thorough with this particular derivation. Another extension of this particular derivation is the expression for transconductance. Here we know that ID is given by the Shockley's equation as IDSS into 1 minus VGS by VP whole square. Differentiating this with respect to gate to source voltage, that is VGS, we get delta ID by delta VGS equal to 2 into IDSS into 1 minus VGS by VP into minus 1 by VP. This is nothing but the simple differentiation that you have already studied in your maths. So now moving ahead, it is nothing but, we know that delta ID by delta VGS is nothing but GM. So I am replacing this particular parameter by GM here. I am retaining this entire term as the same. 1 minus VGS by VP is nothing but the same term written here as 1 minus VGS by VP. The remaining terms are 2 into IDSS into minus 1 by VP. All these three terms together, I am replacing it by GMO. So GMO is nothing but minus 2 IDSS by VP. Observe the minus sign I have taken out common here. 2 into IDSS is the numerator term, and in the denominator I am left with VP. So this is the expression for GM or transconductance. Students, now we move on to the last topic of this particular chapter, that is comparison between FET and VGT. There are several differences between the two. I have listed out a few of them here, the ones that are mostly easier ones. So the first basic difference between BJT and FET is BJT is a bipolar device. That means in case of BJT, current conduction happens both due to electrons and holes. Whereas in case of FET, it is a unipolar device wherein current conduction happens either due to electrons alone or due to holes alone. Hence, it is known as a unipolar device. The second difference is BJT is a current controlled device. Students, remember last year I always used to give you one equation, that is IC is equal to beta times IB. So IC is the output current which is controlled through the input current IB. Here, that is the reason why we call BJT as a current controlled device. Talking about FET, FET is a voltage controlled device. That means the drain current is controlled by the voltage at the input end. Third difference is the input impedance. The input impedance of BJT is quite low when you compare it with the input impedance of FET. FET has a comparatively high input impedance. Since in the operation of BJT, both electrons and holes participate, BJT is quite a noisy device as compared to FET. The noise produced in FET is very less since it is a unipolar device. The next difference is in the power gain. BJT is a low power gain device whereas FET is a high power gain device. Also, BJT occupies more space on IC during the fabrication process, whereas FET occupies comparatively less space on IC during fabrication. These are some of the differences that I have jotted down between BJT and FET. You can of course find a few more. Moving on to the exam corner, students. This particular chapter is targeted for 4 marks with one 1-mark question and one 3-mark question. The probable 1-mark questions are listed below. The 3-mark questions are some of these. So with this, we come to the end of this particular session and we are also done with the chapter of FET. Thank you, students. Have a good day. Bye.